Chapter 32, Electromagnetic Waves. Electromagnetic waves covers Maxwell's rainbow, the traveling electromagnetic waves, the Poynting vector, radiation pressure, polarization, reflection and refraction, polarization by reflection. You can find them in a timeline. Rainbow. Maxwell's rainbow. James Clerk Maxwell's crowning achievement was to show that a beam of light is a traveling wave of electric and magnetic fields, an electromagnetic wave, and thus that optics in the study of visible light is a branch of electromagnetism. Heinrich Hertz discovered what we now call radio waves and verified that they move through the laboratory at the same speed as visible light. It's from Germany. His experiment shows light is an electromagnetic wave. This is the spectrum or range of electromagnetic wave. And this side is wavelength increase, and this side is frequency increase. And you see that one, okay? This is Maxwell rainbow. There's a visible range. It's part of this spectrum, okay? And in this area, look at this area, we have TV, we have communication, and occupy. There are no gaps in the electromagnetic spectrum, and all electromagnetic waves, no matter where they lie in the spectrum, travel through the free space vacuum with the same speed, c. This is Maxwell's rainbow, the visible portion, the red, orange, yellow, green, blue, purple. This is the range is from 430 nanometer, this is purple, red, up to 690 is red. Electromagnetic waves. Some radiation, such as X-rays, gamma rays, and visible light, come from the sources that are of atomic or nuclear size, where quantum physics rules. We restricted ourselves here to a number that equal to 1 meter, in which the source of the radiation, a shortwave radio antenna, is both macroscopic and of manageable dimensions. This wavelength about 1 meter, and the speed is the light's speed of light 3 times 10 to the 8. So the frequency about 300 megahertz. This is the one we studied. Okay.
This radio transmitter and a metal pickup antenna will be used to show some of the properties of electromagnetic waves. When the transmitter is turned on, an alternating current runs back and forth on these antenna rods at approximately 100 million cycles per second. The resulting electromagnetic wave is picked up on this antenna and lights the light bulb connecting the two halves. As the antenna moves further from the transmitter, the light bulb dims. When the antenna is turned at right angles to the transmission antenna, the light bulb goes out.
Generating an electromagnetic wave. This is energy source. This is RLC circuit. They have a frequency, okay? And then we vibrate, you have energy supply for the dissipator because of resistivity. And then the signal transfers through the transformer to this antenna. This is called electric dipole antenna. The two branches of the antenna alternating simultaneously in potential at the angular frequency omega set up by the oscillators. causing charges to surge back and forth along the antenna axis. The effect is that an electric dipole or the electric dipole moment varies simultaneously with time. The traveling electromagnetic wave qualitatively. This is an antenna. Okay, you stand here is a far more distance point. If the observer is at point P, far from the antenna, so that the wavefront sweeping past him would be essentially plane. The variation in E and B at the distance point P. Now, we stand at the P, and the electromagnetic is towards U. And then we observe the electric field and the magnetic field. We see at the beginning, the maximum E up, the B. And then both reduce up to the zero. And then they change direction, they increase, so this both E and the B change direction. And then it reduces to zero and change direction, increase. That's what. Okay? What we found is transverse wave. When the wave goes toward you, E is perpendicular to V. B is perpendicular to V. So electromagnetic wave is a transverse wave. Second, the E is always perpendicular to B. So we have a vector called a Poynting vector, Poynting vector, S equal to E cross B over mu 0. This always gives the direction of the travel of the wave. So you see E cross B, okay, E cross B, 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 okay? This is what we will talk later, Poynting vector. Okay. Both E and B varying simultaneously with the same frequency and in phase. As we shall discuss below, these two waves components cannot exist independently, okay? Change electric field induce magnetic field, and change magnetic field induce electric field. Now, let's analyze. In keeping with these features, we can assume that the electromagnetic wave is traveling towards P in the positive direction of an axis. Now, this is a P. The traveling of electromagnetic waves go to this one, along X direction. Okay, this is why that the electric field in the figure is oscillating parallel to the y-axis. You see the electric field? They're oscillating along the y-axis. And that the magnetic field oscillates parallel to the z-axis. This is a magnetic field. It's parallel to the z-axis. Using a right-hand coordinate system, of course. Then we can write the electric and magnetic field as simultaneously function of position x and time t. So this is how to describe it. E equal to Em sine kx over t. B is Bm sine kx over h. They have the same frequency, same wavelength, same velocity c, omega over k, and same direction. Okay? A is Em, electric field is oscillate along in y x direction, and magnetic field is oscillate at z direction. Okay? A most curious way. One, an electromagnetic wave, let's use the term light wave or light, is curiously different in that it requires no medium for its travel. Mechanics, they need it, okay? But electromagnetic wave, they don't need it. The speed of the light waves was realized to be special. The speed of light in free space had the same value c in all directions and in all inertial reference frame. We know different inertial reference frame, they have a relative speed. They don't have relative acceleration. But when we measure the c, they are the same. That's very strange. A c equal to 299,792,458 meter per second. Actually, what we can do is dot, blah, 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 lot accelerates. And the c, we can treat it as a constant. The meter has now been defined so that the speed of light in vacuum has the exact value which can be used as a standard. Now, this is how we describe this one. This is the lambda wavelength, okay? All electromagnetic waves, including visible light, have the same speed c in vacuum. You will see in the next section that c equal to omega over k. And c, we can prove it. C equal to 1 over square root mu 0 e to 0. We're going to prove it. And also we have to prove it. Em maximum over B maximum equal to C. Now we will prove it in the following section. At every instant and at any point, any location, any time, they satisfy this. The traveling electromagnetic wave, quantitatively, we look at this one. We are going to prove C equal to 1 over square root mu 0 e to 0. And the E maximum over B maximum equal to C. We should now derive above equations and, even more important, explore the dual induction of the electric and the magnetic fields that give us light. That means changed electric field induce magnetic field, and changed magnetic field induce electric field, and then you get the light. Look at this one. The wave traveling along x direction. The E oscillate along y direction. The B oscillate along z direction. Okay, this is the peak. We look at this small curve, okay, loop, okay. This loop is on xy plane, okay. This location is x. This rate is dx. So this point is x plus dx. So this is E, and this is E are different, so we call it E plus dE, okay. And x, E along the y direction, B along the z direction, okay. Suppose this loop has h, height h. Now, what we do, we know E equal to Em sine kx minus omega t, and B equal to Bm sine kx minus omega t. Okay. We take the loop, this anti-clockwise, this one. So its direction A is along the B. We use the right hand, okay. Now, we look at this Maxwell equation. This equation tells us the change magnetic field will induce electric field. Okay. Now we use this one, put this inside. This is loop, we take this loop, okay, this loop, okay. The ds is along this, E is around this. So we write the detail. Starting from here, along this one is h, and this is a constant E, is E plus dE. So this one equal to, this is E plus dV times h. This dx are too small, we just ignore it, okay. They perpendicular equal to 0, okay. The dx is horizontal, E is vertical, the dot equal to 0. And this one, E is up, ds down, so it's minus EH. And then we put this one, you get HDE. Look at this one. Rho phi ln t, or d phi dt, okay? Rho phi equal to b dot a. What is a? This a is area. What is it? H dx. And this is a direction, as we define. This loop is counterclockwise, so a is along the z direction, okay? So this A is dxh. Rho t, they are constant. So we take this out. H dx rho b rho t. Now, we put this detail into this equation. First one is h dE equal minus h dx rho b rho t. H cancel out. You have a minus sign. So this become rho e rho x. This is equal to minus rho b rho t. Okay? And then we put this E and B into it. Rho e rho x, this one. Because the sine kx minus this rho x equal to cosine, and you have a k. So we get this one, E k cosine. See the minus sign, you have rho b rho t. Rho b rho t is here. You get cosine minus omega. And you have originally have minus, 2 minus become positive. You get bm omega cosine. And both cosine we cancel out. We get emk equal to b omega. And so E over bm equal to omega over k. And that is the speed of light equal to c. Okay, so this is the first conclusion. You got to do it. Second, we take another loop. This is a horizontal on OZ. This loop. This loop, we know always we have this equation. This is always. Then we take the loop. This is also counterclockwise. This is x. This is x plus dx. So this is b plus db. This is the b. Now we go this way. Okay, I go this way. All right. ds, the b is negative direction. So this is minus b plus db h. Okay, you look this one. This equation tell you change electric field, induce magnetic field. Now we take this loop. Is this loop, okay? This loop, and then we put d dot ds, b dot ds along this one is the first is this direction. dbs is minus b plus db times h. This two line is dx perpendicular to b, so equals 0, and this one they are the same, so the bh. And then we cancel out BH, you get the minus HB dB. I look this one. Rho phi, rho t. The phi is flux of electric field that equal to E dot A. And this A is this area equal to dxh. Okay? This is A. A is equal to E. This is same direction. So E dot dA equal to EdA. dA is HdA. So rho t, they are constant. Take it out. H dx rho e rho t. So this one equal to mu 0 z0 h dk rho e rho t. Okay? So we get h cancelled out. Rho b rho x equal to minus mu 0 e0 because of a minus rho e rho t. And now we put E and B into this equation. Rho b rho x equal to cosine k bm. This is rho e rho t because em minus omega t. Okay, and you have a minus, you put another minus, you get a 2, cancel out. Okay, cancel out. So you get mu 0 0 em of c. We cancel out cosine. You get b mkt equal to mu 0 v 0 em of c. So em over bm equal to k. Okay, this is k. Okay, over mu 0 epsilon 0 omega for the here, and the k move to denominator. Omega over k is c. So this is equal to c. We know, we just prove it. This is c. So C squared equal to this one. We get C equal to square root 1 over square root mu 0 epsilon 0. This is the second kind of Poynting vector. Energy transport and the Poynting vector. The rate of energy transport per unit area in such a wave is described by a vector S called the Poynting vector. The rate of energy means energy per second and per unit. This is the clear. The Poynting vector. S we define as E cross B over mu 0. We will prove it. Okay? E cross B is the direction. Okay? This is a W. What is energy per second per unit area? The direction of the Poynting vector S of an electromagnetic wave at any point gives the wave's direction of the travel and the direction of energy transport at that point. And SEB here are instantaneous values. The energy associated with the electric field is exactly equal to that of magnetic field. You see, this is the energy stored in the electric field per unit volume. It's defined by half epsilon E squared. We learned from previous section. And you see this E. E is CAB. Okay. And we see the C, omega 0 C. C is square 1 over square root mu kt. Okay? And then we do this one square, you got this epsilon 0 cancel out because half b square over mu 0. And this is what? This is the magnetic energy unit per unit volume. So we see, okay, that energy associated with electric field is exactly equal to the magnetic field. They are equal. Okay. Poynting vector. The rate of energy transport per unit area. Look at this one. This is the energy transport per unit time per unit area. Now we look at this as the direction of the wave transition. Okay, we look at this. This is a square. Unit 1. So the area is 1, and this long is c. So what is this? This is in 1 second through 1 unit area, the energy go in. Okay, so this energy stored in this volume actually is the energy per unit time per unit area. So this one. Okay, this is 1. Okay, now let's calculate how much energy stored in this one. This is should be in unit volume. You have UE plus UB, and the total volume is 1 is C. Okay, then we put this one, and we know UE equal to UB, so this is the UEC then C. Okay, yeah. What does UE? UE is half epsilon E squared. That's equal to E squared epsilon theta C. You know that epsilon C equal to 1 over C mu 0, because C equal to 1 over mu 0 E0 square root. So we put this one here, all right? And then what we find, this E equal to EB mu 0. This is a Poynting vector equal to this one, okay? And E over C is B, okay? It's C over B. And we found Poynting vector S equal to EB over mu 0, or E squared over C mu 0. This is instantaneous energy flowing rate per unit area. That means the energy per unit time per unit area. The intensity of the wave I or the average energy transported over time per unit area is equal to average Poynting vector. And this one equal to E squared of which divided by C mu. What is E? E equal to EM squared sine M squared. Okay, average over C mu. This is a constant. Sine square average equal to half. So we got this one. This is the 1/2 cm. That's what is it? We look at this one. E square over half is the E root mean square over C mu square. And variation of intensity with distance. Well, we have a source S, okay, radiate wave energy. If we look at this, check at a point R from it, the energy, the wavefront is a spheric share, okay, surface. So the total energy divided by the sphere area, the point source emitted the light isotopically with equal intensity in all directions. And then in this direction, the I is energy per unit time per area. P is the energy per unit time, the power, and divided by the area of the sphere. This is 4 pi r squared. That's the intensity at distance r for our point source.
Light from a distant source appears much dimmer than light from the same source seen up close. We'll use this small filament light source and a photometer to demonstrate how the intensity of a light varies with distance. The photometer measures the intensity of light falling on its sensor. When the photometer is 40 centimeters from the light intensity reading is 0.41 lumens. If we double the distance, the intensity is 0.10 lumens, or about 1/4 of the original reading. What will the intensity be at 3 times the original distance? At 3 times the distance, the light intensity is 0.04 lumens, or about 1/9 of the original reading. This graph plots the intensity of the light measured at the 3 distances.
Pressure. Electromagnetic waves have linear momentum as well as energy. This means that we can exert a pressure, a radiation pressure on the object by shining light on it. P, pressure, equal to F over A. F equal to dp dt. P is the linear momentum. Maxwell shows that during the interval delta t, the object gains an energy delta U from the radiation. It also gains linear momentum. If the wave is total absorption, then we find delta P, the linear momentum change, equal to delta U over C. If the wave was totally reflected back along the path, then we found delta P, the linear momentum change, equal double to delta U over C. Sample. When you look at the North Star, you intercept the light from the star at a distance 431 light year and emitting energy at a rate of 2.2.10 to the 3 times that of our sun. This is 3.90 times 10 to the 26 watt. Neglecting any atmospheric absorption, find root mean square values of the electric and magnetic field when the starlight reaches you. We know what do we want to find? We'll find the electric, the magnetic. This is root mean square. This is energy, okay? This energy per unit time per unit area equal to PS over 4 pi r squared, okay? And the PS equal to, this is a sum, okay? This is a sum. This is equal to 3.2 times 10 to the 3, okay? Times sum, PS, 3.9 times 10 to the 3. Okay, we put everything inside. And this should be, by definition, E root mean square over C mu square. Okay? So that one, we can find this one from this equation. E equal to P C mu square over 4 pi r. We put numbers inside, we get the value. Okay? And B, once we know E, B is E over C. Very small. So B root mean square is too small to measure. So usually we measure the E for the light. But anyway, you have to remember the energy stored in the unit volume of magnetic field equal to electric field. To find expressions for the force exerted by radiation in terms of the intensity I of the radiation, suppose that a flat surface of area A perpendicular to the path of the radiation intercepts the radiation. In time interval delta t, the energy intercepted by area A is delta U equal to IA delta t. By definition, I is the energy per unit time per unit area. You multiply by area, by time, you get energy. So, if the light is totally absorbed, then we know F equal to delta P over delta T. Delta P equal to delta U over C. And you put delta U equal to IA delta T in, you cancel out the delta T, you get IAC. On the other side, if the light was total reflect, okay, then F equal to delta P delta T. In this case, delta P is 2 delta U over C equal to 2 IA over C. Let's see the radiation pressure. The pressure equal to F over A. If the light was total absorbed, then radiation pressure is F over A. We cancel this A, is I over C. If the light was totally reflected, then the F is 2IA over C. You divide by the A, you get 2I over C. Changing in linear momentum, okay, summarized, total absorption, okay, is delta P equal to delta U over C. And the total reflection is delta P equal to 2U over C, okay. Delta U is IA delta T, the energy intercepted by area A in time interval delta T, okay. And the force is the change of delta P, the linear momentum derivative, okay. We have delta P, so we have F equal to IAC, because delta U equal to this one, okay, yeah. And total reflection is double. And the pressure, radiation pressure, F over A equal to IC or equal to 2IC. Sample. When dust is released by a comet, it does not continue along the comet's orbit because the radiation pressure from sunlight pushes it radially outwards from the sun. Assume that a dust particle is spherical with radius r, has density rho 3.5 times 10 to the 3 kilogram per cubic meter, and totally absorb the sunlight in the interception. For what value of r does the gravitational force Fg on the dust particle due to the sun just balance the radiation force Fr on it from the sunlight? Now we see that's what balance. So the F radiation equal to F gravitation. That's the balance. What's the F radiation? I got this one. This one is I equal to PS over 4 R. Okay? And then FR equal to IA over C. Okay? This is the energy divided by C. And we have this I is this one. This A is pi R squared. This is radius of the dust. This is over C. Okay? So we can back to the pi R. This pi cancels out. So PS R squared over 4 R squared C. There's different R. This is the radius of the dust. This R is the distance to the sun. And gravitational force is mg/r squared. Okay. And this m equal to rho times 4 pi r cubic over 3. This is R. We make these two equal. What do you get? PSR squared over 4, see this one, equal to GM S rho 4 pi r cubic over 3. And then for the cancel the R squared, we find the big R. The big R is about 3 PS over 16 pi C rho GMS. Okay. So we put number inside. PS is now 3.9 times 10 to the 9, 26 water. Okay. The gravitational force constant is 6.67 times 10 to the minus 11 Newton meter squared per kilo squared. Okay. And the mass of sun is 1.99 times 10 to the 30 kilogram. Okay. And the root density, that's the 3.5 times 10 to the 3rd kilogram per cubic meter. And the C is the speed of light. We put everything inside, we get the R. It's about 1.7 times 10 to the minus 7 million might. Okay. The transverse electromagnetic wave is said to be polarized, more especially plane polarized in the y direction, which means that the alternating electric field vectors are parallel to this y direction for all points in the wave. Okay, we look at it from P point. E is also laid along y direction. This is Z. This is Z. The magnetic field vector are parallel to Z direction, but we focus our attention on the electric field, to which most detectors of the electromagnetic radiation are sensitive. The plane defined by the direction of propagation, the x-axis, and the direction of a polarization, the y-axis, is called the plane of oscillation. The electromagnetic waves emitted by a television station all have the same polarization, but the electromagnetic wave emitted by any common sources of light, such as sun or bubble, are polarized randomly or unpolarized. Unpolarized, the electric field at any given point is always perpendicular to the direction of the travel of the waves, but changes directly randomly. You see, the E can change it randomly. This is the direction that the electromagnetic wave travels, okay, towards you. This is the E. Okay. Mathematically, we transfer unpolarized light into superposition of two polarized waves whose planes of oscillation are perpendicular to each other, but with a random phase difference between them. Now, we treat them as a two oscillation, okay? We'll see. Okay. And the phase difference between these two are random, so you can have this any of them, okay? Partially polarized, its field oscillations are not completely random, nor are they parallel to single axes. We draw one of the arrows of the double arrow representations longer than the others. This one is longer than the other one. So it looks like this direction. Okay. Other ways to produce a polarized light by being reflected from a sheet of a glass or other dielectric materials. 2. By scattering light from atoms or molecules. Polarizer. Incident light wave is unpolarized. When we go through the polarized sheet, only vertical polarized light can pass, or along the axis of this polarization can pass. Components of electric field vector that are parallel to the polarizing direction are transmitted by a polarizing sheet. Components that are perpendicular to the polarized direction are absorbed by the sheet. When originally unpolarized light is sent through a polarizing sheet, the transmitted intensity is half of original intensity. Okay? Because so half was absorbed, half passed. So the I is equal to half I0 intensity. Somewhat less than half intensity is actually transmitted by the real polarized sheets. Law of Malus. You see, if this is the polarized sheet, okay, with direction of its polarizer, and this is the E, okay, which can pass when they go through this polarized sheet, only this part can pass, and this part was absorbed. Since the intensity is proportional to E squared, so we find E vertical, EY equal to E cosine theta, okay? And the intensity is the square. So the intensity passive one is about the original intensity times cosine square theta. This is law of Malus. I equal to I0 cosine square theta. Theta is the angle of this E to the y-axis.
This device consists of a microwave emitter, a microwave receiver, and a bar graph whose length is proportional to the intensity of the microwaves picked up by the receiver. If we rotate the emitter 90 degrees, the intensity drops, then returns to its original value as the emitter is rotated another 90 degrees. If we now place a metal disc with slots in the path of the beam, the intensity of the beam is reduced, but the beam still passes through. If we rotate the disc 90 degrees, the beam no longer passes through the slotted disc. If the disc is rotated another 90 degrees, the beam passes through. This animation shows how the electric field vector of the microwaves is reduced as it passes through the slots. When we rotate the disc to this orientation, currents set up along the metal strips dissipate the energy of the electric field, and the microwave intensity is greatly reduced. These two sheets are examples of polarizing filters. Unpolarized light passing through the filters becomes polarized by selective removal of light with certain polarization directions. If the filters are placed on top of one another in this direction, the light passing through both filters is only slightly dimmer than the light passing through one filter. If we rotate one of the filters 90 degrees, very little light passes through the second filter. Light passes through these two polarizing filters when they are in this orientation, but not when one is rotated by 90 degrees. If we line them up again and flip one filter over, they are still lined up and the light passes through. These two polarizing sheets show the same effect when one is rotated. But when the top sheet is flipped, the light will not pass through. How is this pair of sheets different from the first pair? This animation shows the polarization axes for the first set of polarizing sheets, and how their relative orientation changes as the top sheet is first rotated, then flipped. Here are the polarization axes for the second set of sheets. When these polarizing sheets are in the proper orientation, light can pass through the first sheet, but not the second. If we insert a third polarizing filter between the other two at 45 degrees to both, some of the light now passes through all three polarizing sheets. We will now demonstrate optical activity in Karo syrup. A bottle of Karo syrup is placed between two polarizing filters. As the front polarizing filter is rotated, colors appear due to the optical activity of the Karo syrup. Three uniform cylinders of Karo syrup are now placed in overlapping positions between the polarizing filters. The front polarizing sheet is again rotated, showing areas of uniform color where the light has passed through the same thickness of Karo syrup. Some materials rotate the plane of polarization of polarized light when put under stress, an effect called photoelasticity. We'll place these acrylic figures between two polarizing filters to show the effect. When the acrylic is unstrained, the polarized light from the first filter is not rotated by the plastic, and the plastic is colorless. When we put stress on the plastic figure by tightening this screw, areas of high stress rotate the light from the first Polaroid, allowing only certain colors to pass through the second Polaroid. The plastic now appears colored at the stress points, with different colors corresponding to different levels of stress.
Optical activity and other polarization effects have been combined in an extremely clever and creative way by artist Austin Wood in an art form called the collage. A collage consists of a collage of optically active materials, and it is therefore viewed between two polarizing filters, one of which is attached to the front of the collage. The collage is placed on the front of this light box. The fluorescent light at the rear of the light box passes through a slowly rotating polarizing filter, then through the collage and the polarizing filter on the front of the collage. This example, called Swallowtail, shows the metamorphosis of a cocoon into a butterfly as the rear polarizing filter rotates.
Sample. Fixture is a system of three polarizing sheets, 1, 2, 3, in the path of initially unpolarized light. This unpolarized coming from here. The polarizing direction of the first sheet is parallel to the y-axis. This is the y-axis. This is the y-axis. That of the second sheet is 60 degrees counterclockwise from y-axis. Now, this is the y, the 60 degrees, the second piece. Okay. And that of the third sheet is parallel to the x-axis. What fraction of the initial intensity I0 here of the light emerging from the system, and how is that light polarized? We see this one, after the first one is half, because half was blocked. And from here to here, we use the law of Malus. The angle is 60. So I2 equal to I1 cosine 60 degrees squared. Okay. And this one, they have angle at 30 because it's 60 to 30. Okay. So I3 is I2 cosine 30 degrees squared. Okay. And then we put it together. We find I3 is about 9%, 9.4% of the original is almost nothing. Okay. And refraction. Under some circumstances, waves behave to a good approximation as if they travel in straight lines, being blocked by barriers and casting sharp shadows. And this is called the geometric optics, okay? An approximation that light is traveling in a straight line. This is the one. This is called incident ray. On the surface between air and glasses, two different mediums with different index of refraction. Theta 1 is the angle of incidence. Theta 1 prime is the angle of reflecting ray. And theta 2 is the angle of refraction. This is 2 because it's different medium. This is 1 because they are the same medium. Okay, and we have law of reflection. Theta 1 prime equal to theta 1.
A light bulb with a very small filament will be used to show that light travels in straight lines. Shadows cast by these objects have the same shape as the outline of the objects themselves.
Theta 1 prime.
A narrow beam of
theta
light
1.
is aimed at a small mirror in the center of this disk. This is the angle of incidence of the beam, and this is the angle of reflection. We'll rotate the disk to show how the angle of reflection of the beam varies with the angle of incidence. The angle of reflection is equal to the angle of incidence. This device consists of a microwave emitter, a microwave receiver, and a bar graph display whose length is proportional to the intensity of the microwaves picked up by the receiver. We'll use it to show how microwave radiation is reflected when it strikes a metal plate. If we attach this aluminum plate to the center of the board, the display shows that the beam no longer passes through to the receiver. Rotating the receiver around to the other side of the plate shows that the microwave beam is reflected by the metal plate. The beam is reflected from the metal plate at the same angle at which it struck the plate.
Law of refraction. You had a light shining from a medium 1 with index of refraction N1 to a medium 2 with index of refraction N2. In this case, N2 is larger than N1. So the light shining in and the reflection and refraction, okay? And we have a formula n1 sine theta 1 equal to n2 sine theta 2. You see that n2 is larger than n1. This is larger than this one. So this must be smaller than this one. And so theta 2 is smaller than theta 1 in this case. This is a monochromatic light. It is the index of refraction m equal to c over v. V is the velocity of this light in this medium. Okay. C is the largest, so n is always larger than 1. The index of refraction is dimensionless because velocity, okay, is a constant for a medium, okay. As c is the speed of light in vacuum, and v is the speed of light in the medium in question. If n1 equal to n2, so the theta 1 equal to theta 2, we don't see the refract, okay. Reverse, if n1 larger than n2, n1 larger than 2. So this is smaller than this one. Theta 1 is smaller than the one. You can reflect in this direction. This is some index of refraction, okay? The vacuum is exactly 1. The water is 1.33, okay? The polymer is 1.55, and so on.
When a beam of light strikes the surface of a transparent material, the beam is both refracted and reflected at the surface. This is the reflected beam, and this is the refracted beam. Notice how the angle of each beam changes as the block is rotated. You've probably noticed that a stick appears bent when placed in a glass of water. We'll demonstrate the same effect using these square acrylic and lead glass blocks to make the effect more visible. This stick is lowered onto the blocks with the camera looking straight on, and the image of the stick appears unaffected. When we rotate the blocks, the images of the stick are shifted to the side by a different amount in each block.
When we look at a transparent object such as this glass eyedropper, we can see it even though it is perfectly clear. Differences in the refraction indexes of the glass and air allow us to see the edges of the glass. When we put the eyedropper in a liquid that has the same index of refraction as the glass and fill the dropper with the liquid, the eyedropper nearly disappears.
We'll use these light beams and a mirror to show two different types of reflection. This side of the mirror reflects all parts of the beams at the same angle, and we still have a beam. This is known as specular reflection. The other side of the mirror is covered with a sheet of white paper. If we put that side in the light beams, the light is reflected in many directions, and we no longer have a beam. This is known as diffuse reflection. This animation shows how different parts of the beams are reflected from the two surfaces.
Chromatic dispersion. The index of refraction is not a constant, even for a same material. You like this one? This is the light, okay? This is the red line, this is a blue line, this is wavelength, okay? And you see the index of refraction changes a little bit, okay? It changes a little bit, okay? Generally, the index of refraction in a medium is larger for a shorter wavelength, corresponding to, say, blue light, than for a longer wavelength, say red line. The index of refraction N encountered by light in any medium but vacuum depends on the wavelength number of the light. This implies that rays of different wavelengths have different speeds in a given medium, okay, because N related to V, okay. And then N different, the angle's different. It also implies that rays of different wavelengths are refracted by different angles when it across the surface. Thus, when a light beam consists of compounds with different wavelengths, refraction of the beams at a surface separates the components so that they travel in different directions. This effect is called chromatic dispersion, in which chromatic refers to a color associated with each wavelength, and dispersion refers to the separation of the wavelengths or colors. Monochromatic beams does not show chromatic dispersions, no different wavelengths. Generally, the index of refraction in a medium is larger for a shorter wavelength corresponding to, say, blue light, than for a longer wavelength, say, red light. This means that when white light refracts through the surface, the blue components bends more than the red components, with the intermediate colors undergoing intermediate bending. We have this one, different angle. So, whereas from the air to glasses, from smaller index of refraction to a larger index of refraction, you see this one, this is a straight line. The blue line bend more. On the other side, if you shining the white light from the glass to air, this is a larger index of refraction, or this, and then you see that one, the straight line, the red line also blew higher than the red line. This is written, okay, see the blue line bend more than red line. The most charming example of chromatic dispersion is a rainbow. Okay. You see the rainbow? What happened? Your sunshine, you hit the water drops in the air, and you see that they reflect, and reflect, okay, and then they combine. You see that the red line is on the top, the blue line is on the dot, and it turns out this angle is 42 degrees, okay, and if you can see a rainbow here, the sun must be behind you, okay, and it must be after raining. You have a lot of water dropped in the air. Okay. Well, this is not only chance you can see the wind. You can have another chance at angle 55. This line is called transmit, reflect, and then refracted. Okay, and in this case, you see the red color is in the lower part, and the blue color is on the top part. So in many cases, you can see two rainbows in the sky. Okay, and one is top, one is bottom, and you see the top one, the red one is under what, and the bottom, the red one up top. You can notice that one. They are different structure. Sample. In the figure, a beam of monochromatic light reflects and refracted at point A on the interface between material 1 with index of refraction N 1.33 and material 2 with index of refraction N2 equal 1.77. The incident beam makes an angle 50 degree with the interface. Theta 1, this is a 50 degree. So theta 1 is 90 degree minus 40 degree is 40 degree, okay? Question A, what is the angle of refraction at point A? This one is very simple. We just have a formula, okay? A very simple one. This one, remember, this is a 40, F theta 1. Okay, look at theta 2 is 92. Question B, the light that enters material 2 at point A then reaches point B on the interface between material 2 and 3, which is air, as shown in the figure. This is N3 is equal to 1. Okay. The interface through B is parallel to that through A. Some of the light reflects and the rest enter the air. What is the angle of reflection? Theta 2 prime. What is the angle of refraction in the air? Theta 3. That's a very straightforward formula, okay? Theta 2 is equal to the same thing as this one, this one. This one equal to this one equal to this one, right? Because they are parallel. And we put the equation. And we can get the theta 3, okay? Very simple, straightforward. It's about 59 degrees.
This disk with different colored sectors can be used to show that white light consists of many separate colors. When the disk is spun rapidly, the colors merge into white.
We'll use this disk, called a rainbow disk, to show one way in which the colors composing white light can be separated. When a beam of light enters the disk, it is refracted, then internally reflected, and then refracted again as it leaves the disk. The beam of white light spreads into a spectrum.
Total internal reflection. We look at the source in the medium with index refraction N1. This is glasses, and the interface is glass and air. So N2 is smaller than N1, equal to 1. What happened? We still obey this one, okay? M1 sine theta 1, N2 sine theta 2. The question here is N1 is larger than N2. So we can see theta 1 is smaller than theta 2. See, this one is incident angle, theta 3, theta, okay? And this is refract angle, okay? And refract angle, theta 2 is larger than incident. So when increase the incident angle until the refract angle theta 2 equal to 90 degrees. And what's happening after the incident angle increase? And we find it's the light totally reflects, they call it internal reflection. And this angle, when the reflect angle is 90 degrees, we call it critical angle. When theta 2 equal to 90 degrees, at this angle, we call it critical angle. Okay, and we can find this one, critical angle, very easy, because this is 90 degrees. Okay, so sine 90 is equal to 1, and then critical theta is arc sine, okay, N2 of M1. Sometimes you may confuse N2 of M1 or N1 and 2. I'll tell you a trick. Sine is always smaller than 1. So N2 must be smaller than 1. That's the situation. Optical fibers for optical communication. We know all our communication use the optical fiber now.
Fiber optics cables such as these have revolutionized communications. Here is a larger version of a fiber optics cable known as a light pipe. When we shine light in one end of the pipe, much of the light comes out the other end despite the bends in the pipe. The light is totally internally reflected at the inner surface of the pipe and is thus channeled through the pipe from one end to the other. We'll use this water tank and a parallel beam of light to demonstrate total internal reflection. A chemical in the water fluoresces when the light strikes it, showing the path of the beam. This mirror reflects the beam up to the surface of the water at any angle we choose. When the beam strikes the surface straight on, very little of the light is reflected. At a shallower angle, more of the light is reflected, but most still passes out into the air, as shown by this thread screen. Notice the misalignment between the beam in water and the beam in air. At a still shallower angle, the beam is refracted so much that it becomes parallel to the surface. This is known as the critical angle situation. If the beam hits the surface at an angle shallower than the critical angle, all the light is reflected back at the surface and none crosses through. This is known as total internal reflection. These acrylic tubes will be used to show the type of total internal reflection which makes fiber optics communications possible. When a laser beam is aimed into the end of this tube, the beam bounces off the walls and is guided along the length of the tube, emerging from the far end. The laser beam can also be guided along this curved tube. Real fiber optics cables can bend around corners without losing any of the light passing along them. We now demonstrate total internal reflection of laser light in a water jet. A laser is aligned such that its light passes through a water tank and into a tube at the bottom of the tank. Powdered coffee cream has been added to the water to make the laser beam more visible. When the stopper is removed, water squirts out of the tank into the container below. The laser beam is reflected internally and follows the water jet into the tank. In this close-up view, we can see the internal reflections of the laser beam in the water jet.
At this point too, figure shows a triangular prism of glass in air. An incident ray enters the glass perpendicular to one face and is totally reflected at the far glacier interface. As indicated, if theta 1 is 45 degrees, what can you say about the index of reflection n of the glass? The light, this is the 45 degree. This, okay, must be larger than the total reflection angle, critical angle, okay? All right? So, and the critical angle is sine theta, n2 or minus n1, okay? In our case, n1 is 1, n2 is the glass, okay? Okay, I don't know. This is smaller than 45, okay? Because at 45, it's already internal reflex, okay? So from this one, we get n, okay? Okay, n is larger than square root, but reflection. We see an incident unpolarized rate, okay? When you shine on the surface between air and glasses, okay? And let's resolve the electric field vector of the light into two components. Okay, the perpendicular components are perpendicular to the plane of the incident. And that's also the page of the figure. This one. Okay. These components are represented by dot, letter dot, the yellow dot, okay? The yellow dot. Yeah. The parallel components are parallel to the plane of incident and the page. They are represented with double-headed arrow. There's the head arrow. Because the light is unpolarized, these two components are of equal magnitude, dot and arrow, in this part. In general, the reflected light also has both components, but with unequal magnitude. This means that the reflected light is partially polarized. The electric field oscillating along the one direction have greater amplitude than those oscillations along other directions. However, when the light is incident at particular incident angle, we call a Brewster angle, theta b. The reflected light has only perpendicular component, that's all the dots, no arrow, okay, as shown in the figure. And the reflected light is then fully polarized, perpendicular to the plane of incident. And the parallel components of the incident light do not disappear. They and perpendicular components form the light that is refracted through the glass surface. So in this one, okay, you have perpendicular part, you also have the parallel part, okay? Okay. Brewster angle theta b. In the reflected wave, the parallel component is zero, only perpendicular, okay? This is complete. So it's completely polarized. And the reflected line is partially polarized. Whole the parallel component goes through this one without loss, and some of it perpendicular light. And we have this condition, this from experiment. Theta b, the angle of refraction is plus the angle is refracting is 90 degrees. So we know that's when n1 sine theta b equal to n2 theta r. And theta r equal to 90 degrees minus theta b. So this is become n2 cosine theta b. And from this equation, we can find the theta b, okay, which is move this one, tan the theta b equal to n2 over n1. So theta b equals arctangent n2 and b. You look at this one. When the Brewster teller, the parallel parts never lost anything energy. They turn round. In a glass laser, light must be reflected back and forth through the laser cavity by external mirrors, perhaps several hundred times. Brewster windows are used to prevent beam losses. Like this above situation, the parallel part of light never lost in the Brewster window. Look at this one. You know the parallel part never lost energy at its angle, Brewster.
We'll use this glass plate, a light source, and a polarizing filter to demonstrate polarization by reflection. If we pass the beam through a polarizing filter onto a screen and rotate the filter, the intensity of the light on the screen does not change. The light beam is not initially polarized. If we reflect the beam off a pane of glass, rotating the polarizing filter in the beam causes variations in the light intensity on the screen. The reflected beam is polarized.
Light reflected by a glass surface can be polarized by the reflection. We'll demonstrate that effect using a light source and two glass plates. The light source is aimed at the bottom plate, which reflects the beam straight up. Both the light source and the plate can rotate together, causing no apparent change in the beam. When the beam is reflected by a second glass plate onto the screen, rotating the lower glass plate by 90 degrees causes the light on the screen to fade out. The beam is polarized by reflection from the lower glass sheet, and will only reflect from the upper sheet if the two sheets are in the proper relative orientation. If we replace the glass sheets with two metal sheets, the effect can no longer be seen. Light is not polarized by reflection from metal surfaces.
Next chapter, chapter 33, Images. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.